Hello, Chem 213 students, and welcome back as we cover the second half of Chapter 20, having to do with carboxylic acids and their derivatives. In this second half of the chapter, we're going to cover the carboxylic acid derivatives, the esters, the amides, and the nitriles. And we're going to go on and talk about some of the properties of carboxylic acids and their derivatives in terms of the chemical properties and the reactions that we're going to incorporate into syntheses, and finally review the kinds of peaks that we would see in spectroscopic data such as infrared spectra and NMR spectra. So where we left off last time was we were talking about the reactions of acid chlorides. And with these reactions of acid chlorides, the acid chloride being the most reactive of the carboxylic acid derivatives, can be reacted with a variety of nucleophiles to create a variety of other functional groups, such as the acid chlorides can be converted here to esters, to amides, various kind of primary amide, secondary amide, tertiary amides here. Alcohol, these acid chlorides can be reduced to alcohols. They can be reduced partially to aldehydes. They can undergo Grignard reactions in which we add carbon atoms and convert the carbonyl to a alcohol group. In the case of the standard Grignard reaction here, we can add two of these same groups here to the carbon atom that ultimately gets turned from the carbonyl to the carbon-oxygen bond and with a hydroxyl group here. We can also react here with the so-called Gilman reagent to produce a carbonyl that has one additional carbon atom attached with a group, or it can be multiple carbon atoms, but it's attached here at the carbonyl carbon. And what we're going to see is that this pattern of reactions and the mechanisms that we learned associated with these acid chlorides are going to repeat, and we're going to see them again and again in many contexts. And we'll have a few kind of newish reactions at the end in terms of the amides and the nitriles, but they're mostly going to follow the pattern that we've noticed. So keep in mind some of the two important factors. One was that there's going to be two situations in which reactions are happening, acidic situations and basic ones. And in acidic reactions, you're only going to have protonated and positive intermediates, whereas in basic ones, you will have deprotonated or negative intermediates. So in terms of the synthesis of acid anhydrides, we can create these from acetic acid just simply with high temperatures. This will essentially react with itself. We will lose water, and we've seen that this is another one of these dehydration reactions. So if we have another one of these right here, we'll essentially lose water here. Now, of course, this goes through a mechanism that I'm not showing the details of. It's just that effectively water is being removed, and ultimately the ultimate effect is that this oxygen is going to go and bond with this carbon, and then finally you'll have a bond between this oxygen and this carbon, and you'll get the acetic anhydride. This only really works for acetic acid, this simple mechanism, simple method rather, right here, because most acids will decompose at high temperatures such as 800 degrees Celsius. But this is one way that an anhydride can be produced, specifically an acetic anhydride, which is basically two acetate ions joined by a single oxygen here. So an acetate group here and an acetate group right here. I'm having a hard time tracing that out, but if you want to make this an acetic anhydride, though, there is an easier way. What you can do is take your most reactive carboxylic acid derivatives, the ones we just talked about, the acid chlorides, and we can react them with a carboxylate salt. So here this is a salt that contains the negative ion being a carboxyl ion here, and the positive ion being a sodium ion. And so that makes this carboxyl ion negative. This oxygen is negative in formal charge. It's got 3 lone pairs on it. And so this is going to make it quite a good nucleophile. And so that nucleophile can then attack here at the positively charged carbon in the carbonyl, and then we would have The resonance arrow here showing those electrons going up to the oxygen atom. And that's exactly what you see here. So the attack of the carboxylate ion here, and then the resonance arrow. After that, like before, we're going to have the return of the carbonyl and the simultaneous leaving of the leaving group. And so the leaving group here is chloride, an excellent leaving group, being large and electronegative, thus stabilizing that negative charge quite well. Or you could also say it's the conjugate base of a strong acid. That's another way to evaluate a leaving group, right? Meaning it's a good leaving group. It stabilizes that negative charge well. And ultimately, we have the anhydride that forms. And this can work for not just acetic anhydride with a CH3 here, that's acetic anhydride, but it can be anything, right? Not just R equals not just CH3, it can be other things as well. All right. So notice that in terms of leaving groups, a chloride, great leaving group. A carboxylate ion is also a pretty decent leaving group because of the electrons being on an oxygen, which is highly electronegative, although it's not large like chlorine is, relatively speaking. There is resonance in the carboxylate ion when it leaves. So when it leaves as a leaving group like this, it's not going to leave just like that. But when it does leave, if it leaves as a carboxylate ion, and that carboxylate ion, don't consider this a complete mechanism. What I'm just showing here is when it leaves, there would be other reasons why it leaves, like we saw in the previous mechanism. But when it leaves, you have this carboxylate ion here, and this carboxylate ion has resonance in it. You have an allylic lone pair, so you're going to get this resonance structure right here. That's going to lead us ultimately to this guy. We'll have oxygen right here now with 3 lone pairs. Now there's a double bond right here, and this oxygen has 2 lone pairs. And so there's a resonance between these two, and that is what stabilizes this as a leaving group. So not quite as good of a leaving group as chloride, but quite a good leaving group. And for that reason, it's not necessary to use pyridine with the anhydrides, because we're not going to get a strong acid generated as a byproduct as well. And so if you go back here, you'll notice that when we produce a carboxylic acid from the acid chloride, we need pyridine as a solvent if we're reacting with water or with an alcohol here. But that is not necessary for when we're having the leaving of the carboxylate ion here and the hydrolysis of this reaction of this acid anhydride. So we're going to have basically an analogous diagram here. It's all the same. The one difference here being for the reaction with this water and with this alcohol right here. Notice there's no pyridine, right, as a solvent. But otherwise, it's exactly the same as we saw for the acid chlorides. If we react with the alcohol here, we get the loss of the carboxylate ion here and the replacement at this carbon here with an alcohol that is then deprotonated, giving us an ester. So here the alcohol is a nucleophile. Here we have the ammonia being a nucleophile here, and again the carboxylate group leaving. All the mechanisms are going to be analogous to those of acid chloride. It's going to behave very much the same way. So you'll see that these are all the same reagents here. With the formation of the acid chloride from the alcohol, again we react with some base here, and to deprotonate the acid here, making it a carboxylate ion, and then it can attack an acid chloride. This represents an acid chloride. So that's just describing what we saw here. The base here creating the carboxylate ion, and then the carboxylate ion doing a nucleophilic attack on the acid chloride. Okay. Acetic anhydride here is often used to acetylate an amine or an alcohol to make an ester or an amide. So here, for example, we have an alcohol. Again, we react the alcohol with the acetic anhydride. The carboxylate ion leaves. We get a replacement here of that entire carboxylate ion with the OR group being a carbon here, and we get an ester. Or if we use a primary amine, we get, with an acetic anhydride, we get here this amide with one carbon atom attached to the nitrogen. Acetic anhydride can be used commercially to synthesize aspirin and Tylenol. So again, this is another alcohol, so just remember the way this is working. The mechanism is the same as with the acid chlorides. So if we have, again, an alcohol as a nucleophile here, the alcohol being the nucleophile with these 2 electrons, it's going to do a nucleophilic attack. We're going to have the resonance arrow here going up to the oxygen. And then there's going to be a second step, which I'm going to just draw in at the same time. We have, after that, the recovery of the carbonyl and the leaving of the carboxylate ion. And so at that point, we've attached this part, 2 carbons here, and this carbon being double bonded to the oxygen. This part, which is in red, right here, that is these guys right here. This oxygen, this carbon, and this methyl group attached. Likewise, we can do a similar thing to produce Tylenol. So Tylenol can be this para-amino phenol here, the amine here. The amine is going to function as a nucleophile in this case, and it's a primary amine, and it's going to do a nucleophilic attack again on this carbonyl group. We have the resonance arrow that goes along with this, and then in the next step, which I'm drawing in blue here, we recover the carbonyl, and then the ester leaves as a leaving group. So again, it's this part that is drawn in red right here is then produced. And again, I kind of combine these 2 steps in one just for simplicity's sake, since we've already seen this mechanism. It's just a reminder that this also works with acetic anhydrides in the same way as it would have worked if we had a if we had a chloride. Whoa, where did I go? Oh, I went way ahead. Same way as if we had a chloride here, right? Except except it's commercially it's a little bit better to do this. Proceeds a little nicer, and so this is what's actually often used. It's also that acetic anhydrides are just a bit more common. So practically speaking, this is a good way to synthesize them, and that's what's used industrially. So we can prepare esters also by the use of the carboxylate ion in an SN2 reaction. So what we can do is these carboxylic acids here are, quite acidic. So what we can do is use sodium hydroxide to deprotonate them, and then they will do an SN2-like mechanism on an alkyl halide. So this will occur in 2 different steps here. And so just to kind of go through the details here, we would have hydroxide, which would come from the sodium hydroxide. We'd have sodium ions too, but we don't care about those. Okay, and this would first deprotonate, so if we have a little bond here between the oxygen and the hydrogen, what we're going to do is we're going to do a proton transfer. So this is going to grab this proton, and then these electrons are going to go on the oxygen, and this is going to produce for us a carboxylate ion. Now this oxygen has 3 lone pairs and a negative formal charge, and at that point we can do a SN2 type mechanism on methyl iodide. So we have CH3I, and so note that this is a primary alkyl halide, so there's very little steric hindrance for the backside attack here of the carboxylate group on the carbon. So we have a nucleophilic attack here, and the loss of the iodide as a great leaving group there, and ultimately we get this methyl group right here, which I'll circle in blue. That is what's now attached to this oxygen atom here, yielding us the ester. So you can use a base followed by an alkyl halide to make esters as well. There's another reaction here that can produce esters. It's known as the Fischer Esterification, and this combines the carboxylic acid and an alcohol, and using an acid catalyst here. And so we know that alcohols, they're not great nucleophiles, right? And so we may need to kind of help it along in terms of attacking as a nucleophile, right? So if we have this methanol, we want this to attack as the nucleophile, but this is not a great nucleophile. So we can help this reaction along with the acid catalyst, because instead what's going to happen is we'll start by protonating this carboxyl group here, which makes it even more, as we've discussed in the previous chapters, it will make it even more susceptible to a nucleophilic attack here. And then we'll have a series of steps that will ultimately lead to the ester, and we're going to go through that mechanism now. Okay, so as I said, this is going to be catalyzed by an acid, and so what's shown here is actually a little bit different. It's that if we have hydronium, let's say we have some acid, right, which we represent with hydronium here, and if this is around the methanol can, to some extent, be protonated by this acid that's been introduced, right? So we'd have a proton transfer here, this methanol grabbing a proton, then leaving these electrons behind, and this gives us this protonated methanol. And so that's what's going to be written as the source of the protons for this mechanism. So again, we start by protonating the carbonyl, which makes it even more susceptible to a nucleophilic attack, even by a weak nucleophile like methanol. And so now the methanol nucleophile can attack. It'll attack the carbonyl carbon, and simultaneously, as we've done many times before, we'll draw the resonance arrow here. Now that gives us oxygen at the top here, returns it to an alcohol by giving it two lone pairs, and now two bonds, one to the carbon, one to the hydrogen. And at this point, we have a protonated methyl as well. Whoops. Oh, geez. Oh, gosh. Okay. We have a protonated methyl group right here. Oh, whoops. Sorry. I skipped around and lost my place. And there we go. Okay. So now we've got this this note that this neutral nucleophile attacked, and so when a neutral nucleophile attacks, like in the case of this oxygen, it uses this lone pair to create a bond. So now it has three bonds and one lone pair, giving it a positive formal charge. So the next step is that the methanol, which is likely to also be the solvent as well as the reagent here, this will deprotonate, and this will return to us our acid, essentially. And that's why we say it's acid catalyzed. So this is what, what we're using as our acid here, the protonated methanol. We've now recovered our protonated methanol. And so at this point, this oxygen now once again has two lone pairs and two bonds, one to the methyl group here and one to the carbon that was part of the carbonyl. At this point, what we want to complete the formation of the ester is we still have to have one of these oxygen leaves, and we have to have the reforming of the carbonyl. And so for the alcohol to leave, it's going to have to be protonated to become a good leaving group, to leave as water. And so we're going to have a proton transfer between our regenerated protonated methanol and the alcohol group here. And so now this methanol returns to being deprotonated, and we now have a water leaving group ready to leave. And so this is where we recover our carbonyl. We have a resonance arrow here, essentially because this leaving group is leaving at the same time. It's leaving as water, so we can say, minus H2O if we want. We're losing water. But now this oxygen has a double bond, and it has a bond to hydrogen. Right here, a double bond, because these two electrons now are pi electrons. And we have one bond to hydrogen here and a lone pair, giving the oxygen a positive formal charge. Finally, this is not stable until it's neutral, right? And so we have to recover our acid catalyst. So the methanol is going to come over and it's going to grab this proton again and leave these electrons behind on the oxygen, now giving it 2 bonds and 2 lone pairs. And so we get now the finalized ester here. And so a really analogous mechanism to what we've seen, right, previously as well. We always start here. In this case, we've got acid, so when we're in an acidic environment, generally we're going to start with the protonation of the carbonyl. We have the nucleophilic attack. If a neutral nucleophile attacks, it needs to be deprotonated and neutralized. Finally, we have the protonation of the water so it can leave, and the recovery of the carbonyl. So the mechanism for this Fischer esterification has been supported by research, obviously, into which atom is going where. And what they find is that if they isotopically label the oxygen and then they look for the presence of that oxygen by its radiation that it's giving off in the product, it will appear as this oxygen in the ester that's produced. So Fischer esterification also can be controlled, whether it goes forwards or backwards, whether you produce the ester from the carboxylic acid more, or you take the ester and then hydrolyze it and get the carboxylic acid back. It depends on how you control the reaction. So the way this reaction is driven forward is the water is removed from the mixture, and so if we remove the water, then the equilibrium will go in the direction to replace that water. And so if we have excess of methanol, the reactant here, and we're removing the water, this will drive this reaction quite far forward. In addition, we saw previously that esters could be prepared by treating an acid chloride with an alcohol. Again, that works in a similar way, except we don't have to have as much complicated protonation and deprotonation. We don't need an acidic environment because the acid chloride's more reactive than the ester itself, and so we can have the direct attack of the alcohol. But with the acid chloride, we need the pyridine because that's going to deprotonate. When our neutral nucleophile attacks here like this, it's going to be protonated, right? And so after that, the chloride leaves and we end up with the protonated alcohol. The pyridine is here to deprotonate that alcohol and get it back to neutral, finally giving us the ester. So the first step here would be the nucleophilic attack, and then we would produce this one right here. I'll just say carbon, oxygen, and then we still have the chloride. We have the alcohol attached here, and this has a positive formal charge. And I got to delete here. This now has 3 lone pairs. This has 3 lone pairs and a negative formal charge. And finally, we need the pyridine in order to deprotonate that. So the pyridine has a nitrogen atom. I can deprotonate this. And then finally, we get the ester. And the oxygen will have 2 lone pairs. At this point, it had 1 before. Now it has 2 and it's neutral. So notice the big difference there, right? In the Fischer esterification, we use acid to catalyze it. We made the carboxylic acid more reactive here, but we ultimately had to deprotonate at the last step. So we needed this pyridine solvent here to do that. Esters can undergo hydrolysis under basic conditions. Now, this is called saponification, and it's called that because that's the way soap is made. Soap is made by this reaction here of esters, triglyceride esters, with sodium hydroxide here, lye as it's also called, and then a final protonation to produce the neutral salt. And so you're going to note that this reaction proceeds very much like we've seen, but we have to keep in mind now this is in basic conditions. So we can't have any positive ions. Our hydroxide here is going to behave as our nucleophile. So the first step is going to be the hydroxide coming in here and attacking the carbonyl carbon. and then the reaction will proceed from there, and the ester group will leave as the leaving group, or the alkoxide group will leave as a leaving group. So here we have a nucleophilic attack by the hydroxide, just as I said, in the resonance arrow here, leaving us an alkoxide ion as we're used to seeing. Now, this alkoxide ion is equally as unstable as any other alkoxide ion about. So what we're seeing here is that there's going to be pretty even equilibrium, but enough so that this alkoxide ion returns to being the carbonyl, and we get the loss of the OR group as an alkoxide ion, because now the oxygen here will have not 2 lone pairs but 3. It will have a negative formal charge, and now we have produced a carboxylic acid. And so this carboxylic acid, it's much more acidic if it has a negative charge, because if it gets deprotonated and it has a negative charge, it will stabilize that negative charge very well. So you can see that this reaction for this last step is a one-way arrow, because now we have produced for us quite a much more stable anion after this deprotonation occurs. Basically, the carboxylic acid is a much stronger acid than this resulting alcohol, and so this reaction is going to go very far forward. We're going to have the deprotonation of the carboxylic acid, giving this oxygen 3 lone pairs, 1 bond, a -1 formal charge, and now we have the protonated alcohol. So this is why now we've treated with sodium hydroxide. That was the first step, but notice that we were not done hydrolyzing this ester and getting the carboxylic acid. We still need to protonate the carboxylic acid. So there's one last step where we now treat with acid. So this was all step 1. Now step 2 is going to be very simple. We're going to treat this with acid, any kind, really, and we're going to now have a proton transfer, right? This is going to transfer here, and then we'll have the protonated carboxylic acid, and that's what's shown here, along with the loss of the leaving group here, which was the methoxy that ends up being protonated by the resulting carboxylic acid and becoming methanol. And this mechanism, we write it again with a one-way arrow because that last step isn't really reversible. We get a much more stable carboxylate ion here than we had with the methoxy ion. Okay. So in terms of the mechanism, now here what we did is under basic conditions we produced the carboxylic acid from the ester. We hydrolyzed the ester. We produced the carboxylic acid. What about another way? What about under acidic conditions? Can we hydrolyze the ester under acidic conditions as well as basic conditions? So again, the name here for the acid decomposition here of this ester into the hydrolysis of the ester under basic conditions is referred to as saponification. The hydrolysis under acidic conditions is just the hydrolysis under acidic conditions. It's the reverse of the Fischer Esterification. And remember, there were ways to control the Fischer Esterification, right? I think I misspoke earlier. We can control it by controlling the concentrations of the methanol versus the water, as we had discussed before. So notice in the last reaction, this was base catalyzed. We never had a positive ion, right? Keep that in mind in your mechanisms. That makes it so it kind of drives you to making sure that you always have these negative ions here in the mechanism. Whereas when it's acid catalyzed, the carbonyl is going to be protonated and make it a better electrophile here. And so we have first the protonation of the carboxyl oxygen here, and so this oxygen now will have not only its double bond but a bond to a hydrogen and one lone pair, so that gives it a positive formal charge. And now this makes it susceptible to attack by weaker nucleophiles like alcohols and water. And so we have the attack here of water, and then we have this resonance arrow here showing now the oxygen having 2 lone pairs and 1 bond here, and now we have this neutral nucleophile that attacked. So once it attacks, this oxygen atom is now 3 bonds with one lone pair, giving it a positive formal charge. So the next step here is going to be to deprotonate that alcohol here, or the water, and turn it back to an alcohol. And this is going to recover our acid catalyst here. Okay, and at that point, the methanol here is protonated. So you can see, again, this is the exact reverse of the Fischer Esterification. We're doing every step basically in reverse. This is getting protonated by the water here. So there's a proton transfer. This oxygen now is making 3 bonds, one to the hydrogen, one to the carbon, one to the methyl group here. But because it's protonated, that means that when it leaves, it will leave as a neutral alcohol, making it a much better leafing group than leaving it as an alkoxide ion, or in this case methoxide ion. And so we have the reformation of the carbonyl, the carbon double bond oxygen, and the loss of the methanol here. And finally, the last step is the recovery of our acid catalyst and the return of our neutral carboxyl group by having a proton transfer from water and these electrons now residing on the oxygen, giving it a double bond and 2 lone pairs there. And so notice that this is the exact reverse of the Fischer Esterification, right? If we go back and look at that mechanism, we can see it. In that mechanism, we have the protonated methanol. It attacks, we deprotonate it. Then we protonate the water leaves, and then we deprotonate the carbonyl. In this case, it's just the exact opposite. Here we protonate the carbonyl, just like before, but now the water attacks, and now the water's protonated, so it gets deprotonated instead of the methanol like before. And then the methanol gets protonated, and then it leaves as a leaving group like the water did in the esterification, and then we get the protonated carbonyl, which has to be deprotonated. So it's just the exact reverse of the Fischer esterification. And remember, we can control that by controlling the amount of water we have versus methanol. If we're taking out the water and adding more methanol, that will drive it towards the esterification. If we're adding in water and taking out the methanol, like right here, then we can drive the reaction the other way. Okay. In terms of esters and their reactions with amines to produce amides, they behave in a very similar way. The equilibrium here will favor the amide formation. The amides are more stable and thus less reactive than esters. Remember from our ordering of them. Remember, it was acid chlorides first, then acid anhydrides, then esters, and then the amines being the least reactive. And so we can make these amides from esters. This will involve another nucleophilic reaction, nucleophilic attack on the carbonyl carbon, this time with ammonia. That said, the synthetic utility is limited because this isn't as strongly spontaneous as would be the reaction with the acid chloride. The acid chloride is much more reactive than this ester, so it would be preferable really to react the acid chloride with the ammonia, and we'd get the same result, right? But it also can be done with the ester because the amide is more stable than the ester, so that will support this reaction moving forward. In terms of the reduction of esters, we can reduce the esters just like the acid chlorides and the anhydrides with lithium aluminum hydride, and we'll reduce that carbonyl to an alcohol. It's going to be the same type of mechanism as we saw before. We're going to require two equivalents of lithium aluminum hydride. We're going to get two alcohols produced. Here are the 2 separate alcohols, and the mechanism is really just the same as the reaction with the acid chloride. So just reviewing that, remember that the reduction by lithium aluminum hydride always involves a transfer of a hydride ion. So the hydrogen is leaving with both its electrons this time. This is not a proton transfer, right? This is a nucleophilic attack of a hydride ion. And then this lone pair here will go on the oxygen. At that point, we'll have 3 lone pairs on the oxygen and 1 bond, giving it a -1 formal charge. At that point, we're going to have the leaving of the methoxy group here, and we'll simultaneously recover the carbonyl. So now we have reduced to an aldehyde. Now with lithium aluminum hydride, it's not going to stop there. It's going to continue to reduce this if we have two equivalents here. And so again, we'll have a transfer another hydride here, and then the lone pair here going on the oxygen. At that point, we have a deprotonated oxide ion. This alkoxide here, we'd want to treat it with an acid, so in a subsequent step. So this would be the first step, this would be a second step here. We'll treat it as a workup with acid afterwards, and we'll have a proton transfer, now protonating that and getting us the alcohol. So these two hydrogens came from the lithium aluminum hydride, the aluminum hydride here, and the last proton here came from a second step where we added acid. Now, you may not want to reduce the ester all the way down to the alcohol. Maybe you want to stop when you have the aldehyde. And that's perfectly valid. And as we saw before, we can use a sterically hindered aluminum hydride, of which there are a couple. It was written very generally as just having R2ALH. But here is a more specific reagent that's often mentioned called DIBA. It has these two sterically hindered isopropyl groups here, making it a little bit harder to give over that hydride ion the second time. And so you can force it to stop here at the aldehyde. You follow up with the protonation using water to protonate this and finally or protonate the alcohol and finally get the alcohol and the aldehyde. You can also use a Grignard reagent as a nucleophile, and you can add two carbon groups here, two of the same, and ultimately get an alcohol. So remember, what the Grignard is good for is adding carbon atoms and getting an alcohol group at that same carbon atom where you added other carbon atoms. The reaction here is going to be the same as for other nucleophiles, or the Grignard with the acid halide. There's no difference, so I'm going to go through the mechanism again, but really it's exactly the same. In the end, we're again going to get a deprotonated alkoxide ion, which will then be protonated here with water. And so it's going to involve, remember the Grignard here, when we have this, it's like having a R minus here and an MgBr plus. And so the R minus is a nucleophile that attacks, and so we're calling this R minus here, whatever it is, whatever carbon atom chain it is. It attacks at the carbonyl carbon, and then we have the lone pair here on the oxygen, giving it three lone pairs, one bond, a -1 formal charge. Now we're going to have the loss of the methoxide leaving group here in this case, and then we're going to have the recovery of the carbonyl bond. At that point, there's still carbonyl, so it can still undergo nucleophilic attack by this strong nucleophile, the Grignard, and so it will attack the carbonyl again. And again, we have that resonance arrow putting the lone pair up on the oxygen, giving it a -1 formal charge. And then that's the end of the first step. Then we're going to go on to the second step. And this is where we have to protonate the alkoxide ion that was produced. And we can do that by adding water or something protic that can provide protons. And we have a proton transfer. And finally, we get the protonated oxide. And we have hydroxide as well as a product. So there will be a kind of equilibrium there. And that's going to be it for this video here. So that's going to finish up the reactions here of the esters and the anhydrides and the esters. Sorry, I'm kind of skipping around here. That's going to finish the reaction of the anhydrides and the esters. When we go into the next slide step, we're going to talk about, or the last video of this week, the second and last video, we're going to talk about the reactions of amides as carboxylic acid derivatives, and also the reactions of nitriles. And finally, we'll say a little bit about how you might use these reactions in subsequent synthesis problems, And finally, we'll have a short review of the kinds of spectral features we'd see in IR and in carbon NMR and in proton NMR. So I'll see you in that next video.